Okay, so let's do another optimization example, section 3.7. Here we have a rectangular box with an open top is to be constructed so it has a square base. The cost of the materials for the base is $5 per square meter, and for the sides it's $3 per square meter. Remember, there's no top, right? So it's just the bottom and the four sides. If the volume of the box must be 180 cubic meters, then find the minimum cost to construct the box, right? So, yeah, so the idea is we're going to construct a box. Oh, hang on. So let me try to draw a box here. Actually, before I do that, I'm going to make sure this works. Sorry about that. All right, so a box, right? I'll do the best I can. Right, vaguely resembling a box. Let me try that piece again here. Okay, right, and then you have this part over here. Okay, so a box, right? So we have the length of the box, the width of the box, and the height of the box. So I'll just call those L, W, and H for length, width, and height, right? All right, so let's read this question again because I think I just messed this up. A rectangular box with an open top is to be constructed so that it has a square base. So this base I drew here is not exactly a square, is it? So for it to be a square, it might look more like this. And then the height might be something else. Something more like this. Oops. All right. So in other words, the length and the width have to be equal here. So if the length and width are equal, why don't I just call them both x? Right. And then the height, I'm going to call that h. I'll use lowercase h for the height of the box, right? Okay. So that's our box. So what do we need? We need the cost and also the volume of the box. I hope you know how to calculate the volume of a box, right? Well, in general, it's length times width times height. But in this case, the length and the width are equal. So x times h, or just x squared times h. Now, what do we know about the volume? It has to equal 180 cubic meters. So what does this tell us? This gives us a relationship between x and h, right? This is our secondary equation. Okay, this is how x and h are related. Okay, so we're going to use that later. Let's go back and figure out the primary equation. Okay, so the primary equation has to do with what are we trying to minimize? We're trying to minimize the cost, right? So this is going to be cost. So I'll use C for cost. And what is the cost? Well, it's $5 for each square meter for the base. Now the base, that's this piece down here, and it's just a square, right? It's just a square, x meters by x meters. So the area of that square is, well, x squared, right? So whatever that area is, let's say it's 10 square meters, if x is square root of 10. So maybe let's suppose x is 5, right? If x is 5, this is 25 square meters. Well, if each square meter is $5, what are we spending here? 25 square meters times $5 per square meter is going to be $125. And that's just for the base here, right? We have to worry about the sides as well, right? So yeah, the cost is going to be $5 times the area of the base, right? And I was using as an example that x is 5, but I don't think that's going to be the answer here. In other words, I would be surprised if it is, but it could be. Right. So that's the cost of just the base here. Oops. Hang on. I need to do that. Right? This is just the base, the square base. But then we also have the four sides here, right? So we have the side on the left, the side on the right, the back, and the front. So those four sides. What do we know about those four sides? Well, let me try that again. Let's use the back as an example here. It's a rectangle, right? The length is x and the height is h. So the area of this rectangle is just, well, length times width, x times h. But notice we have four of these, right? The back, the front, and the right and the left, right? So the total area is going to be 4xh. Okay? So that's the area, right? But how much does it cost per square meter? It's going to be $3 for each square meter. Right? So that's going to be the cost of the four sides. Right? So when you multiply all this out, you just get 5x squared plus 3 times 4 is 12, so 12xh. Okay, so is everyone with me so far? Right, so now we have our cost. This is the cost function, and this will, basically, if we know the base, the x and the height, we can calculate how much it's going to cost, right, based on this function here. But notice that this function depends on both the length and the height. It's a function of two variables. I don't know how to take the derivative of that. Well, I do know, but it's a much more complicated story, right? When you have a function of two variables, yeah, you're taking what are called partial derivatives, but we're not going to do that here. The story is, right, what we have to do, of course, is reduce this down to a function of one variable, right? In other words, we have to find a relationship between x and h. And in fact, we did that already. Remember, we already found the secondary equation. It's this. X squared times h equals 180. Okay? So we already have a relationship between x and h, right? I kind of did that first, but now we need this, right? So now going back to our cost function here, or our primary equation, right? This is our primary equation. We have to reduce it down to a function of just one variable, right? And the way we do that is very similar to what we did with the rectangle problem. We have to solve for either x or h, and then plug that in here to get this to be a function of either x or h. So if you want to solve this as a function of h, you would solve this for x. But I kind of prefer, just because we're so accustomed to having functions of x, to have this as a function of x, right? So why don't we solve this equation for h? Hang on. If we solve this for h, we get h is equal to 180 divided by x squared, right? Just divide both sides by x squared. So if that's h, that's the same h as this h right here, right? So now we can just plug that in. The 5x squared, that's not changed. That stays the same. Plus 12 times x. But now h is 180 all divided by x squared. Okay? So what we do now is simplify this, right? We're going to simplify this, and I'm just trying to do some arithmetic in my head here. Maybe I'll bring up a calculator. All right, 1 second. All right, so my C of, oops, sorry about that. The stylus has a mind of its own. There's a little button here that's right where it shouldn't be. All right, so C of x, again, 5x squared. We knew that. And then 12 times 180. 12 times 180 is 2160. Oops. 2,160, right? Divided by, not x squared, but x divided by x squared is 1 over x, right? So in other words, one of these two x's cancels here, right? Then make that clear. This x cancels with one of these x's. and you just get 2160 over x. All right, so now we have this down as a function of one variable, right? So this is our primary equation. Now we can actually call it a primary function because it's a function of one variable. And what do we want to do? We want to minimize it. We're trying to minimize the cost here, right? We want to build this box for the lowest amount of money possible. So how do we do that? Well, find the critical numbers, right? So we need the derivative. We'll call it c prime of x, right? And so this is just going to be 10x. And then you can use the quotient rule here, or it might be more helpful to write it this way. Plus 2160 times x to the negative 1. Now you're just using the power rule, right? So you're going to get negative 2160 x to the negative 2, or if you want to write it as a fraction again, minus 2160 over x squared. So that's the derivative of the cost function. So set it equal to 0 and solve for x. Those will give us our critical numbers. So I think we can solve this pretty easily. We get 2160 over x squared, right, is equal to 10x. So multiply by x squared, and you get 10x. That's an equals 10x times x squared is x cubed equals 2160. Divide by 10, and you're going to get 216 for x cubed, right? So x cubed equals 216. And so to solve for x, you just take the cube root of 216, which I think is 6. Don't quote me on that. Hang on, I'm just double checking on my calculator here. Yep, 36 times 6, 216, right? So there we go. We have our critical number, right? Our critical number is x equals 6. And since there's only one, what can we say? It better give us a minimum cost, right? So how do we know that it's a minimum and not a maximum? Well, we can use the first derivative test or the second derivative test. At this point, I think they're both just as easy. Yep, let's do the second derivative test again. So take the second derivative, so that's just going to be 10. Let's see, so 216 times 2 is 432, right? So I think we're going to get plus 4,320 times x to the negative 3. I think that's it. Yep, I think that's it. So, right, so now just plug in 6 here. Oops, there it goes again. So if we plug in 6 into the second derivative, well, I'm not actually going to calculate this, right? The important thing here is that we have a positive number plus another positive number. It's positive. So what do we know when our second derivative is positive? It's concave up. So at our critical number of 6, we know we have a relative minimum. And so that establishes that we do get a minimum cost and not a maximum. Okay, but again, let's answer the question, find the minimum cost, right? So the minimum cost is, well, the cost function is up here, right? C of x, this up here. So now we're just going to plug in x equals 6 to get the minimum cost, right? So the minimum cost will be the following. C of, 6. So 5 times 6 squared plus 2160 divided by 6. All right, calculator time. So 5 times 36 is 180. 180. And then 2160 divided by 6, I think is 360. Yep, 360. So hang on here. Plus 360, which gives us a grand total of 540. Right. Now 540 what? These are dollars, right? So we're going to spend $540 to build this box. Yeah, expensive box, right? But you know, I mean, this is a huge box here. I don't know what this is made of, some sort of, you know, metal or something that's just very expensive, or maybe an expensive wood. But at least in this problem, that's how much it's going to cost. Now, they didn't ask us this, but they could in some questions. What are the dimensions of the box, right? Well, we already know that the base, right, the x's here are going to be 6 meters, right? So x is going to be 6 meters. And then h, how do we find h? Right here. We have the formula for it, right? 180 divided by 6 squared. So 180 divided by 36. 180 divided by 36 is 5. So, yep. So 5 what? 5 meters. So the dimensions, if they ask for the dimensions, we can say it's, 6 meters by 6 meters by 5 meters. So 6 meters for the base, and then the height is 5 meters. And of course 6 times 6 times 5, of course, gives us 180. It better be, because that's the volume that the box has to be. It has to be 180 cubic meters. They didn't mention that. 180 cubic meters. Right, so they didn't ask us that in this problem, but be careful, because in other problems, they might not want the actual cost. They might say, find the dimensions of the box which minimize the cost. So if that were the case, then they'd ask us for the dimensions, 6 meters by 6 meters by 5 meters. So length, width, and height. Does that make sense? Okay, so this I'd say is a fairly typical problem, right? It takes getting used to, but once you do a few problems like this, this I would classify as kind of a standard medium type question. It's not easy, but it's not one of the more difficult ones either, right? So maybe for the next video I'll do a more difficult one than this one, if you can imagine that.